We'll now round out 11.5 by talking about absolute convergence. And this is where we really start to formalize and bring together the ideas that we started talking about in the beginning of this section, but also from the very beginning. Which is to say, if we talk about the alternating harmonic series and the harmonic series, right? Remember that the alternating series converges to ln of 2, but the harmonic series diverges. And if we think about this as call the whole thing a sub n, including the alternating part. And so we can think about the 1 over n as being the absolute value of each term, right? So another way of thinking about it then is absolute value chops off the negative sign if it's present and leaves the term intact if it's positive. So the link here is that the harmonic series is the absolute value form of the alternating harmonic series. So we would say that the alternating harmonic series conditionally converges but not absolutely. So let's break down what that means. We say that the series a sub n is absolutely convergent if the corresponding absolute value series converges if the series itself converges, but the absolute value version diverges, we say it is conditionally convergent. Okay, so visualizing this is actually not super tricky once we get a grasp of the definitions. You can think of starting with some series, a sub n, and basically asking the question, does it converge or diverge? And that basically classes it into two categories. So it is either convergent or divergent. And if it's divergent, then we don't need to go any further. But if it's convergent, then we can ask another question, which is it convergent absolutely or conditionally? So both of these are different flavors of convergence. And you'll notice then we are really saying that absolute convergence is a stronger form of convergence, okay? So here's a lemma, or a result that, kind of comes from the definitions, kind of not. If the original series converges, then, converges absolutely, then the series converges. Regular converges. This is confusing because we're using the same word sort of twice, but remember that there's two different levels to this, which is absolute convergence is a kind of convergence. Convergence itself broadly speaks about both of these kinds, right? So let's justify this. Here's the idea. For all n, a sub n plus the absolute value of a sub n is less than or equal to 2 times the absolute value of a sub n. Okay, why is that true? So let's think about this side of the inequality first. A sub n plus absolute value of a sub n is either 2 times absolute value of a sub n because a sub n is positive, or a sub n is negative, and so then that equals 0. Make sense? Okay. So it's either 2 times absolute value of a sub n or 0, which means it's definitely less than or equal to 2 times absolute value of a sub n. And so the idea then is, if a sub n is, the series is absolutely convergent, then the series consisting of just the absolute value terms is finite. So in other words, this is finite, this is finite, and so this is bounded by something that's finite. It must be finite as well. So this is a very loose justification. To make this precise, we'd have to talk about other things, but we're not going to. Let's see how this applies in action. We're going to determine whether the series starting at n sub 1, negative 1 to the n over third root of n, we're going to see whether that converges absolutely, conditionally, or diverges. So to answer this question, right, where do we know where to start? We actually are going to start backwards from this diagram that I drew. So this is how we separate all the different series into what kind of flavor of convergence it is, or divergence. But to test a series for these different kinds of convergence and divergence, we actually would start from the innermost circle. So test for absolute convergence. So either it is absolutely convergent and we're done, or it's not, and then we have to test for conditional convergence. And then if it's not conditionally convergent, well then it's definitely divergent. Does that make sense? So let's start by looking at the absolute value. So we're going to test for absolute convergence by looking at the corresponding non-alternating series. So negative 1 to the n, third root of n, and absolute value just means basically we're going to chop off the negative 1 to the n power. So this is 1 over n to the 1/3. Okay, this is a p series. P series with p equal to 1/3, less than or equal to 1. And so this diverges. So, in other words, our conclusion here is not absolutely convergent. Why? Because the corresponding absolute value series is not converging, so it can't be absolutely convergent. It could be conditionally convergent. Let's test that. So we're going to now apply the alternating series test by looking at just the part of the term that we care about. This is a sequence that decreases monotonically to 0. Not hard to see that this is true, right? By the alternating series test. The original series, not the absolute value version, but the alternating version of it, converges. So that's where we're at. That's where we're at. This is conditionally convergent, which is a convergence. So it converges, just not absolutely.